Okay, so meeting again with Mateusz Łewyk from Warsaw, who will continue his lectures on non-equivalent axiomatization of PA and Tarski boundary. Welcome, Mateusz.
Thank you, Roman, and thanks for your patience with to continue with the third installment of this talk. Let me quickly recapitulate
let me just say that when we had this not online, I think I went on record. I was talking about something, and I gave like 7 or 9 lectures about one thing.
Loftiness.
We have loftiness. We have patience. We're patient people, or at least some of them.
Challenge accepted. Okay, so the main character for us is the following axiomatic theory of truth, and it is a very straightforward axiomatization of the inductive Tarski condition. So it has 4 axioms, each of which gives a commutative clause for the respective connective or quantifier. So the basic setup is that we start with some arithmetical theory, and over it we build an axiomatic theory of truth, and these will be our basic axioms. So we can further extend this theory with induction, in which case we denote it with CTN. If we add sigma and induction for the extended language, we call it CTN, and CT is the full theory. And I don't think that they will be needed in this talk particularly. And we will focus on the theories over PA. So since we are about to extend this theory with a single sentence saying that all axioms of PA are true, then we can as well think about CT minus. We can also think about this theory as built over, say, EA, to make the syntax work reasonably. Right. So by itself, CT minus is conservative over PA, and more generally, CT minus over T is conservative over T. So these purely compositional axioms do not add more arithmetical strength. However, already CT0 is very non-conservative, and it has certain incarnations which will be important for us. So first of all, CT0, so delta zero induction for the compositional truth predicate, can be equivalently axiomatized with a global reflection principle. What is even more important for the purpose of this talk is that it can be equivalently axiomatized by the global reflection over pure first order logic. So observe that in contrast to the first point, the analogous arithmetical principle, so uniform reflection over logic, is provable in PA. So maybe let me
Mateusz,
more. Yes.
Since there are only a few of us, and I usually feel like asking some silly questions, but in a bigger audience I don't, because you never know how silly they are. But
great.
Not just about this number 2, so this or maybe even number 1. So you quantify over all 5, but
overall arithmetical sentences.
Right. No, I understand. But do you get any sort of weakening of these things when you restrict the 5s to some subclass of certain kind of sentences? How about if you restrict their complexity, for example?
And this is a very good question. So I mean, certainly, so I'm now improvising, but I think that saying that the truth predicate agrees with sigma n sentences, it can be arranged quite cheaply. So it does not give us more strength. So I suspect that the respective global principle for all sentences. We will quantify only over sigma n sentences, but it will be arithmetically weaker, and it will be conservative over sigma n uniform reflection. So, so you simply take a model to prove conservativity. You simply take a model of sigma and uniform reflection and build over it elementary and extend it to a model which agrees with in which to a model of CT minus in which T agrees with the set of true sigma n sentences, and this and then you have this restricted global reflection.
No, I suspected that, you know, if you do the restrictions to some well-known classes of sentences, that is probably well classified and well understood. But what if we just sort of say, well, I just want certain kind of theorems to be true, but I'm not quite sure, you know, what kind of sets. In other words, do we really need them all? You know, because all theorems are not that interesting. Maybe it's enough to have some. And but anyway, it's a vague question, and I just wondered if anyone thought.
So let me maybe an answer in this direction. So we have an observation joint with Ali that, for example, you can have equivalent. You can replace global reflection with the statement saying that all provable, all schemes provable in PA are true. So whenever you have a scheme which is provable in PA, then every its instantiation is true. So this is equivalent to CT0 as well.
And single sentence is not considered a scheme.
And I would have to think, that's a good remark. I would have to think about. I mean, okay. So this is a slightly different principle. So it is if for all psi it is provable in PA that phi of psi holds.
I see.
And I think that it has to be quantified also.
Well, but phi of psi
could
be. But
yes, phi of psi can be as well. So yes, so I would have to go. Sorry, I would have to go back to this, and maybe Ali can help me out with.
The only comment that in connection with Raman's question is if we take a phi in number one to be ranging over even quantifier free, then we could get, for example, we can pick phi to be falsum, you know, some contradiction. And then that would imply that PA is consistent.
All right.
So already, so already by choosing the lowest possible level for phi, we get something stronger than PA. Okay. But but I don't know off the top of my head whether that already gives you. That would be kind of surprising. It gives you CT0. So that's, yeah, it's a very nice question.
But okay, so let me also no, sorry, I'll have to go because so normally we're focusing on restricting these theories for which we have a global reflection, not classes of sentences. But yeah, this is a yeah, I think I don't have any much more interesting to say in this respect. So I will think about it. Maybe something will come to my mind later on. And crucially, also we have the following principle that every coded disjunction of formulae over an arbitrary coded set, if it is true, then there is a true member in this set. This is called disjunctive correctness out. So it suggests that the capacity of decoding these infinitely long disjunctions, it gives us a lot of arithmetical strength, and it's also, I mean, also a sign for me that it's not that far from. So conceptually, truth theoretically, it's not that far from CT minus to the global reflection principle, because the last item seems to be very weak. But quite surprisingly, it's arithmetically this is very strong. So in particular, if you compare this to this our previous discussion with Roman, so if in the first item in this theorem you restrict these phi's to sigma and sentences, then the respective principle prove sigma and uniform reflection, and that's all. So in a sense, summing over n's, that's obviously quite a naive way of reasoning, but well, naturally, this theory should be something like uniform reflection. And it gives us, I mean, from the arithmetical point of view, and it gives us each finite number of iterations of uniform reflection. So arithmetically, this is quite far from CT minus to CT zero, and truth theoretically, this is not that far. And yes, so what we do, and in the project, we want to understand this area between CT minus and CT zero. So in order to do this, I mean, the approach I'm going to present, constantly presenting, is to isolate a natural family of a family of natural extensions of CT minus, and prove some structural results about this set of extensions. Yes, so each of these theories will extend CT minus with the assertion all axioms of a certain axiomatization of PA are true. So let me recall what do we mean by, so these axiomatizations should be internally correct, meaning that PA should be able to verify that all the sentences in the chosen axiomatizations, they are really equivalent to its own, say, canonical presentations. And in order to make this more appealing, I'm using the notion of proof theoretical reducibility. So recall that one, say, formula thinking as formalized theory is proof theoretically reducible to another one, delta to delta prime, if and only if I sigma 1 can prove that whatever is provable in delta, it is provable in delta prime. And we shall focus on deltas which are proof theoretically equivalent to the usual axiomatization of PA. And let me introduce a piece of notation. So we shall study families, theories of this form, CT minus over EA, to make it a finite theory, plus a single sentence for every X. Every sentence from delta is true, where delta ranges over various proof theoretically equivalent axiomatizations of PA. And goal for today, we look at the conservative side of the Tarski boundary. So we are going to say, conservative side, on the conservative extensions of CT minus. And the goal for today is to check how different can various theories of this form be if you assume that, if you restrict to conservative extensions of PA, or more generally to a given arithmetical theory provable in CT0. So the theorem we shall focus on is the following one. There exists a family, essentially there exists an an infinitely branching tree with infinitely many levels. So the nodes of this tree will be identified with finite sequences of natural numbers, such that each of these theories, so nodes of this tree, will be decorated with theories, and each such theory is conservative over PA. If two theories lie on the same branch, and one is above the other, then the one which is above is strictly stronger. And if two theories lie on incomparable branches, then their union is a non-conservative extension over PA. And in fact, as I warned you last week, this is a work still in progress, and I think that today I'm able to present this proof in a slightly more elegant way, and I mean in such a way that this theorem is no longer a mystery, and it's believable that much more difficult patterns, I think, can be found in among these, if you focus on these theories. So let me introduce two notions of key importance, and if any of them rings a bell, then please tell me, because I mean I just isolated them starting from this project, but I think that they're somehow natural, so probably they were studied. So we look at family of formulae which probably in CT- isolate a progressive set of numbers. So it is closed under successor, probably in CT-. And we say that this family of cuts is independent if for every model of PA and every subset of this family, we can find an elementary extension of this model in which any cut from the set H is the shortest possible in this model, i.e. is the standard cut. And quite to the opposite, all the other cuts, they cover all the model. I mean, not jointly, but each of them covers the whole model. So in a sense, the idea is that we have a family of formulae, and we can, in a sense, independently turn them off and on, where turning off means that they are short, and turning on means that they are blown up to the whole model. And the second notion, which will in fact play a key role in distinguishing between various theories, is the theory which is made true on a definable cut. However, this is not, I mean, simply the theory of this of the definable cut, but it's the theory consisting of all universal closures of formulae which are provably universally true on this cut, or more generally a formula. So if we have a formula with one free variable, we say that the theory of theta in this theory T is the first order theory axiomatized by all sentences of this form, such that T proves that psi universally holds restricted to this formula. And we'll use it for theta being provably a cut. Okay, are there any questions?
So just a quick comment. This second definition, because a theory usually is associated with a class of models, but because of the completeness theorem, what you're writing down is equivalent to the other definition of a theory, meaning, or am I missing something?
I mean, Okay, so
or I guess you're looking at maybe just the universal. Yeah,
I'm abusing the notion of a theory, but so I mean, we take a theory,
yeah,
which has as axioms all sentences of the form. So it closes the probability.
okay,
right? So
yes.
that's my. So I think that in this way, this is. Well, this is. Yeah. So sorry. Does that answer your?
I think so,
question?
because if we take, let's say, the theory T and the formula theta, and then we look at all models of T, that gives you a bunch of models of arithmetic, and within each of those models, we could look at the cut that theta is describing.
Mm-hmm.
Is your typical theta is going to be a cut? Maybe that's, I should ask that first.
Yes. I'll use it for a cut.
Okay.
Yes.
So I give so beginning with a model with a particular theory T, we look at the class of all models of this theory. We get a lot of models of arithmetic. In each model, we look at the cut described by theta. That gives you now little models within these models, and we look at what are the sentences that are true in all of them.
Okay, so this is not exactly this. So yeah, so this is maybe slightly less natural, because in a sense, in this formula, you're relativizing to theta only the first universal quantifier. We are not relativizing all of the quantifiers to theta.
Okay, yes, okay, then I'm with you now.
But just the first one. So the idea is that, so think about a true pi01 sentence, which is not provable in a theory T, which is which can nevertheless, I don't know whether it is possible, or in an extension of a theory. No, okay, so sorry, it's possible. So it is not provable in a theory T, but nevertheless can be made true. I mean, within T, you won't find a within theta, you won't find a counterexample to this sentence.
Okay. Yes.
And in the case, for example, in the case of pi2, it means that you are saying that each guy in theta has a witness, but the witness can be outside.
Right. I'm now with you. Okay, very good.
Sorry, can I ask a question as well?
Yes.
This in this first definition, this family of cuts, are we insisting on some sort of uniform definability? Like, is there, right? Is it like one formula which with like data of xi, so that data of xi defines x's and ii, and so is there some sort of uniformity in this definition, or
I think that after all, we'll be interested only in recursive sequences of cuts, meaning that the function assigning to each I its definition should be recursive, but the definition as it is, I mean, is fairly general, and I think it's, I mean, for the purpose of this talk, it's not needed in this generality, but just not to complicate more things at the beginning, I wanted to just give it in a totally abstract way.
Okay, thank you.
Right. So let me now. So, in fact, the way to get this theory CT minus square brackets delta will be will consist in defining a family of an independent family of cuts, which are provable in CT minus, and then defining these theories so as to each of them prove that on a certain cut, a certain theory holds, which is stronger than the theory which on this cut is provable in the previous theory, and so on. So let me now, I mean, I will go back to it. Probably this was vague and not that much helpful, but the construction of this theory will be essentially about forcing a theory, forcing in a non-technical sense, forcing a certain theory to be true on a cut from an independent family of cuts. So let me now say a few words how I'm going to generate a family of independent cuts for CT minus. So disjunctions. So we have a model of CT minus and we have a subset of sentences in the sense of this model. And we say that this model trivializes A if for every sentence in A, every binary idempotent disjunction with phi is true. So this means this means writing a disjunction whose syntactic tree is a full binary tree of height A, and this tree has formula phi written at every leaf. So it looks just something of this form, and here we have phi, syntactic tree of phi. Okay, so we have phi hidden, perhaps non-standardly deep in this junction, and we say that empty trivializes the set A if for every sentence from this set A, every non-standard, this pleonastic disjunction is true, and we say a dual notion. So empty is disjunctively correct on B if for every phi, every idempotent disjunction is guessed correctly. So we say that for every x, the disjunction, the idempotent disjunction with phi is true if and only if phi itself is true. So disjunctive correctness on B in this context means that the disjunctions, arbitrary long disjunctions, are idempotent with respect to if you take disjuncts from the set B. Right, and this is the crucial lemma. So it will be the generalization. It is the slight generalization of the independence lemma I gave you last time. In fact, I need a slightly more general version. So if we have a model of PA and two formulae, arithmetical formulae, possibly with parameters, such that, I mean, it is true in M that in the union of the sets defined by this theories, we have only sentences, and none of the sentences is a disjunction. And more importantly, the sentences in theta 0 are essentially different from sentences in theta 1, which means that in particular, no sentence in theta 0 has the same syntactic tree as a sentence in theta 1. So this is sufficient. And then you can find an elementary extension of M, and in this elementary extension, an extension of a CT minus truth predicate, which makes all axioms, all traditional axioms of P, all axioms of induction true. This is what I mean by CT minus square brackets PA. And NT is disjunctively correct on the set defined on theta in N, on the set defined by theta 0 in N, but it trivializes all sentences defined by theta 1 in N. Right, so note that we started with formulae, we defined certain sets in M, then we moved to an elementary extensions, but we want certain that these sets satisfy certain conditions with respect to n. But I mean, both 1 and 2 will hold in n as well by elementarity. So, I mean, this is the generalization of the trivialization lemma of Bartek, which I used during the first part of this talk. Basically, it is if you take theta, sorry, which one? Theta 1 to be the set of all sentences and theta 0 to be empty, then you get this Bartek's lemma that every non-standard model of PA has an elementary and extension in which every disjunction of non-standard length is true. And here I would like this model N to be smart with respect to some sentences and totally dumb with respect to some other sentences. And once again, this is, so the proof of this is a modification of the Enayat and Visser construction. I can say a few words at the end why the proof is not that hard modification of the standard Visser construction of the infinite chain of models. Good. So now let me outline the proof idea of the main theorem. So we shall construct, so we first imagine this infinitely branching tree to be decorated firstly not with theories, but with certain formulae which are cuts. So first, think that at each node of this tree, you have a cut which comes from an independent family of cuts. Let me maybe make it slightly bigger. Right. I mean, and so on and so forth. And so the first condition is and then I'm going to associate with this tree a family of deltas. And these deltas, we can think about these deltas that they say something about the cuts which are written at the nodes of this tree. So, I mean, first of all, probably it's sufficient to take a probability in PA. Delta G is a subset, is a subset of delta F. So not only, and this is important, I mean, each of them will be proof theoretically equivalent to PA. So I sigma 1 will prove that all sentences, all delta G theorems are also delta F theorems, but we would like here that they be subset with respect to the usual inclusion. So as said, delta G is a subset of delta F whenever G is strictly lower than F in this tree. Right. So the second thing. So if we have two comparable nodes in this tree, then a bigger node, now suppose that we are here in this tree, and here we have a cut written, and here we have also as well a cut associated. So this theory will tell that the cut associated with this node, and this node on this cut, con-PA holds. the third point is that basically the cuts higher up in the tree, they are in a sense not interesting. So they are, what is true on them is just PA. I mean, observe that PA is true on since the theories extend PA, and then by definition, PA is a subtheory of the theory of every cut in this theories. And most importantly, if you, maybe not most, but the third point is that if you have incomparable nodes, so for example, if you look at this guy and this guy, and they are right, and they are at the same level, perhaps, sorry, let me focus on guys, on the, this is not precisely what is written in here. So it should be the case that if they extend, if they have a common parent, immediate ancestor in the tree. So for example, this guy and this guy. So this guy proves that the cut associated with this node is everything, and this guy proves that the cut associated with this node is everything. So if you combine the second and the fourth item, then you get that any such two theories which has the same common ancestor, the union of these two theories proves CUN-PA, because the first one says that PA holds on this cut, and the second one tells that, I mean, this cut is everything. So PA is consistent, and vice versa. Okay, and this first condition, this monotonicity condition, assures that this will happen whenever you take any two incomparable nodes in this tree. So then you just go back to their common ancestor, not necessarily direct, and you use the fact that these smaller theories, they are provable than the bigger theories. So, okay, so that's the idea, and I would like to proceed to the details. So are there any questions? Okay, if not, then let me continue. So I think that yes. So the above conditions guarantee that 2 and 3 from the thesis of the main theorem hold. So the 3 was that the union of incomparables is non-conservative, and I said already. The 2 said that whenever F properly extends G, CT minus over delta F will be a proper sub-theory of CT minus over delta G, and this is because of the first item. So bigger theories in this tree, they are stronger. They are, sorry, not weaker. And the combination of the next two, the second and the third, tells us that actually each theory which is higher up in this tree proves that PA is consistent on a cut, which cannot be proven in the theory which were lower in the tree. Okay, so so if you have a branch in this tree and you look at this theory, so there is a cut associated with this theory, IF, and there is a cut associated with this theory, IG, and CT minus over delta F proves that PA is consistent on this cut. CT minus over delta G proves that CT minus is consistent on this cut, but CT minus over delta G does not prove that CT minus is consistent on this cut, and that's why they will be different. And we will heavily rely on independence in guaranteeing these conditions. So let me pass to the construction. So first of all, we need sentential representations of nodes in this infinity branching tree. So I mean, each node can be identified with the following obviously true sentence. It is a conjunction, and the first conjunct is 0 equals 0, preceded with 2 times f of 0 negations. The second disjunct is 0 equals 0, preceded with 2 times f of 1 many disjunctions, and so on and so forth. So each such so the syntactic tree of this sentence uniquely codes certain finite sequence of natural numbers. And we write PF of send to denote the set of conjunctions of PF and arbitrary sentences. So this is like a translation of the set of sentences by the sentence PF. So for every sentence in this set, every sentence in this set is a conjunction, and the left conjunct is simply this formula. So look that if F and G are different, then PF of send is syntactically structurally independent than PG of send. By structurally independent, I mean that the syntactic trees of sentences in PF of send are different from syntactic trees of sentences in PG of send. And finally, the cut. The cut says that truth commutes with idempotent disjunctions, so IF, on sentences from this set PF of send. And yes, so probably in I sigma 1, if F is different than G, then PF of send and PG of send, they are structurally independent. This is what I already said. In particular, we have our family of independent cuts by the independence lemma. Right? So we can take the family IF indexed with finite sequences of natural numbers, take an arbitrary subset of this family, and then thanks to the independence lemma, we can put all PF of send from one set into theta 0, all PF of send from the second set in theta 1, hence trivialize disjunctions over one set and find a model on which T is disjunctively correct on the sentences from the second set. Okay. And now the definition of delta F. So we define delta F as the union of PA and the following set. So the first set gives us the consistency condition. So it says that whenever I'm a sentence, I mean, almost. So first approximation. Whenever I'm a sentence belonging, I mean, the consistency statement conjuncted with PG, and this conjunctive with PG is just to make all these sentences structurally different. Then the nth binary disjunction, the binary disjunction of depth n of such sentences is true. Note that this n and this n is in fact the same, right? So in particular, this is a standard disjunction, is a standard sentence if and only if n is standard. However, observe that we cannot simply put to delta all sentences of this form, because this is not proof theoretically reducible to PA, because internally it implies that PA is consistent, right? Because no number is a proof of contradiction. And sorry, once again, so this comp restricted to n is a finitary consistency statement, which says that no number below n codes a proof of the inconsistency of PA. Okay, so this is, in this case, this is a delta zero sentence with a parameter. And we consider also in non-standard models, we consider non-standard parameters as well, right? So that's why we use the safety condition. So we say that this holds provided that that high is provable, is a logical tautology, and it is false. Okay, so and some things. So note that this he is independent from n. So for every, in fact, for every such antecedent, we have all succedents of this form. Okay, so I will tell you why it works, because I'm going to present the proof soon. I mean, on the next slide. But this is also the trick I used during the first lecture. And the second set, is that is just that the junctions are idempotent with respect to sentences from PG of sent, where G is not too long and it is incomparable with F. Right, so in fact, this condition is not that important. Note that all such sentences, they are propositional tautologies. So they are provable in PA, and I sigma 1 knows it. Right? Good. So this is the definition of delta F, and now let me continue with the proof. So let me now show you that for every F, CT minus square bracket delta F is conservative over PA. Okay, we fix an arbitrary model of PA, and we apply the independence lemma to the following two sets of sentences. For the first one, we take theta 0. So these are the sentences we would like to be disjunctively correct on. And we take all PG of sent for G which is not below F. So this is more than we need, in fact. But I will also use it to draw some conclusion later on, right? And in theta 1, we take all sentences of the form PG conjunction a sentence for G which is below F. So now observe. Independence lemma gives us an NT, which is a model of CT minus square brackets PA, and we claim that in fact it satisfies CT minus square brackets delta F. So we fix an arbitrary sentence from delta F and we consider cases. So either it belongs to this first set. The first set, this consistency set, then each sentence in this set was of the form, if something holds, then a disjunction of sentences PG con PA up to N holds. So I claim that each such implication from this set has a true conclusion. And this is because if this conclusion is a non-standard disjunction, then it is true in this model by the independence lemma, because this sentence which this disjunction, the sentence that the disjunction has as leaves in its syntactic tree belongs to PG of sent by definition, and we trivialized this set in NT. Okay, and the second option is that this disjunction is standard. It is. Then we are dealing with. Okay, so maybe let me recapitulate it and write it because it's. So phi is an implication where here is something that does not interest us, and in the succeedent we have a disjunction of sentences of the form con PA up to A. So this sentence, so PG is something obviously true, and if A is non-standard, then this sentence is possibly false in our model, because there might be, we took an arbitrary model of PA, and there might be a proof of contradiction of PA below this A. And in such a case, this sentence con PA of A is false. However, in this case, this A is non-standard. And in our model, all non-standard disjunctions of sentences of this form are true by the construction. Okay? And the second subcase is that this A is standard, but then con PA of N is provable in PA, so it holds in the model in particular is true, right? So phi is in this case, phi is an implication with a true conclusion in the sense of this true predicate T, right? So we took care of the first component of this set. And the second thing, I mean, if phi is in the second component, then phi is of the form psi is equivalent to the disjunction over psi of arbitrary length for some n in the model n, possibly non-standard, and psi in PG of sent where G is inconsistent with F. And we are working in CT minus over delta F, right? However, note that all such sentences, they are in theta 0 in NT. So our model, so for every such sentence, our model satisfies the generalized commutativity condition. Right? And applying compositional clauses, we get that phi is true, in fact. Okay, so this witnesses conservativity. And what's more, observe that since in here, we were disjunctively correct with respect to all sentences in PG of send, for G possibly bigger, possibly larger than F, then it witnesses that this theory CT minus square brackets delta F does not prove anything interesting about this cut IG where G is larger than F, right? Because we've taken an arbitrary model of PA and we've shown that in this model admits an elementary end extension in which this cut is everything. Right, so nothing interesting except for PA can hold on this cut. Great, and two more steps. I mean, I hope, great. Right, so we are, let us show the consistency on the cut, and here we'll make use of this antecedent that we put in conf PA. So we show that if G is a subsequence of F, then CT minus square brackets delta F prove the consistency of PA on this cut IG. So we fix G and any MT, which is a model of CT minus square brackets delta F. And here we are using the distinction by cases as in the main theory of the first talk. So if this model satisfies CT0, then we have conPA in this model, and we are done. So conPA holds. In particular, it holds on every definable cut. Otherwise, and this is where I'm using this characterization of CT0 as CT minus plus uniform reflection over logic. So if this is not a model of CT0, then we can find a he, an arithmetical formula he, which falsifies uniform global reflection over logic, right? Such that it is provable but false. Okay, so in particular, by considering the sentences in this set conf PA, for every A in our models, it holds that such disjunction is true. Why? Because in our set, every sentence of this form belongs to delta F by the construction, right? So it is every sentence of this form is true according to T, and every sentence of this form has a true antecedent. The assumption of this implication is true, so the conclusion has to be true as well. Okay, but this witnesses that in fact on this cut we have conPA, right? So since every such disjunction is true, so if A is such that T commutes with disjunction of length, with disjunctions of I should say def A for such sentences, then for such A, the sentence is true. So CT minus square bracket delta F proves the consistency of PA on IG. And I think that okay. Let me also show that it is not that maybe needed, but I mean, it will be good. So nothing, in fact, nothing more is provable with respect to this cut in CT minus square bracket delta F. I think that's not needed in the construction, but this is always good to have an accurate characterization. So we take an arbitrary model of PA plus conPA. And now, by the independence lemma, we can take its elementary extension to a model of CT minus square brackets PA, which is disjunctively correct with respect to all sentences. Right? And in such a model, this cut IG is everything. So in particular, our theory cannot prove any independent from PA plus conPA, and it cannot prove that any independent of PA plus conPA sentence holds on this cut. And this concludes the proof, right? So to sum it up, so we wanted, let me go back. We wanted the following properties, and they are true by, the first one is true by the definition of delta, by the definitions of delta F. The next two were just proven. That they have been. I've just proved them. I mean, and the last one is trivial because we included in delta F for G inconsistent with F. We included all the sentences of the form which the disjunction over psi is true if and only if psi. So this witnesses the fourth item. And are there any questions with respect to this proof construction? If not, and if I can continue for 6 more minutes, may I?
Sure.
Of course. Then one more easy consequence of what I shown you that so we can fix this will correspond to the speed up of these theories of this form. So we have a single CT minus definable cut. Okay, so now we forget. So this won't be about independent cuts. Now we have just one cut, such that for every arithmetical pi2 sentence and arithmetical RE theory, such that both the sentence and this theory is provable in CT0, we can find a delta such that CT minus square brackets delta coincides with T on arithmetical sentences. So it is a finite axiomatization of T. And on this cut, CT minus square brackets delta makes this pi true. So in particular, since I is a cut, and you can take P to be a sentence of the form, there exists a value of a terribly fast growing function, and PA is consistent up to this value, this gives you a theories with a very large speedup. In particular, you can show that for every f alpha from the fast-growing hierarchy of functions, which so that the totality of this function is provable in CT0, there is a theory of this form which has super f alpha speedup over PA. Where having super f alpha speedup over PA, it means that there is a family of sentences, of arithmetical sentences, which are provable in both T and CT minus square bracket delta. And if you take such that the proof of this, sorry, let me write it. If you look at the proof of the phi n sentence, let me write it in CT minus square brackets delta. So you look at ratio of the size of the in T. So to look at the size of this, the size of the least proof of phi n in CT minus square brackets delta, and you look at the size of the least proof of phi n in T, then it will be smaller than, I mean, in the limit, then it will be smaller than 1 over f alpha of n. So it means that this proof in CT minus square bracket delta will be really, will be much shorter asymptotically than proofs in T. Okay, good. So this is all I wanted to say, I think. Yes, thank you very much.
Thank you, Mateusz. Now we clap. So, and it's time for questions. Ken?
I do have a question.
Sure.
Yes, this is very, very elegant work, and there's a lot of finesse and detail. But my question is, it's a long question. The question is, how much does it really depend on arithmetic, on Peano arithmetic? And I ask that because there's another theory which is very much like Peano arithmetic, that's ZF. ZF is reflexive, it proves the consistency of all the subtheories. It has a lot of the features of Peano arithmetic, including there's a theory of cuts, or a notion of cut with models of ZF, like rank extensions and the end extensions. And using infinitary languages, you also have a girdle theory. You have recursion theory on sets, and you have girdle incompleteness analysis. So my question is, you know, how much does your work depend on the fact that you're dealing with arithmetic, and could it extend to models and structures of ZF set theory?
Yes, so this is a very good question. So so let me think. I guess that right. So some characterizations of this, say, right. Let me go back to show you the first. The first difference. I mean, this theorem fails for ZF in particular. So
Mateusz, which one?
Sorry, the theorem. Sorry, not the first one, the second one.
Second.
This with 3 items. So in particular, delta zero induction is really weak. So perhaps we should have then delta zero separation. Okay, good. So let me now, because I'm now recalling some thoughts we had joined with Ali, Bartek, and Cezary about it some time ago. So I think that this fails for ZF as it is, because you can show that CT minus with full induction period for omega, this is conservative over ZF. And this is not that maybe surprising, because full induction is it's weak in the context of set theory. However, if I remember correctly, then perhaps with the exception of the third item, this can be recovered if you add that all axioms of separation, sorry, not separation, of replacement are true. Because the replacement is what is problematic in the context, problematic, is what is strong in the context of truth theories over ZF. In particular, you can show that CT minus plus full separation is conservative over ZF. This is the classical work of Krajewski from 70s, I guess. Sorry, Ali.
It's Krajewski's proof, but basically looking at the proof, it becomes clear that it gives the result you just mentioned. Yeah.
Yeah. So I guess that as long as we assume that all axioms of all instantiations of replacement are true, then we should have the equivalent between CT0, 1 and 2. So in particular, it might mean that the theorem from my first talk can be recovered in this context. So it says, however, it is in a sense not that surprising, because once again, uniform reflection, right? So one should think about what is what is uniform reflection over ZF, whether one works, whether one allows for names for sets in the form, say, of domain constants, or so. But I think that some version of the theorem from the first talk, which says that every say now every set theoretic theory between ZF and all finite iterations of uniform reflection appropriately defined over ZF can be axiomatized by a theory of this form. And now these different theories, and I would have to go carefully through this proof. I mean, it seems possible that all these tricks can be recovered, since you can work with models of ZF which have non-standard omega, and then it should be the techniques should be similar. Although, I mean, this is still talking about the more simple-minded generalization, and in particular, there is an interesting case which you alluded to with infinitary languages, and I think that we are still planning to look at it, but that it's not yet clarified what you can do with truth theories for infinite languages of this form.
Well, thank you, and thank you for a very engaging performance in improvised mathematics on the fly. Very impressive.
Thank you. Thank you for your kind words.
So I guess that's probably it for today, unless Ali, Attar, any questions? Okay.
I was just wondering if Mateusz has, having done this beautiful work, if there are one or two natural questions that have opened up as a result that you're working on in connection with basically you looked at outside the Tarski boundary and inside the Tarski boundary.
Mm-hmm.
In terms of refining any of these results, or is there any kind of natural path that is the next step?
Okay, so yes. Right, so I think that right now it would be great to show so possibly it will be possible, for example, to embed rationals, the rational structure, ordering structure, in the set of CT minus over delta being conservative over fixed T. I would have to think about it and then investigate some universality properties of this ordering. So this gives us, I mean, that we can embed every countable linear order in the structure. And then we can say what about more general, what about partial orders. Also, an interesting question, so my conjecture is also that using this way you can go, in a sense, below CT minus square brackets PA. So in this talk, I also always extending this theory, which says that all axioms of induction are true. However, I think that it is possible using these independent cuts to find theories CT minus over delta, which are probably below, which are strictly weaker than this theory and still incomparable.
Okay.
This is, I mean, a straightforward way to do it is to consider axioms of induction only for formulae which are disjunctions, which are along the junctions of certain formulae. And then possibly you can then build a trivial model in which every formula of this form is true, and then standard is true, which would make this theory true in this model, and then pushing the analytic construction, you can also force this model not to be a model of full internal induction. That's the idea. And a very interesting question also in this context, but I do not have a clear strategy of attacking it right now, is to have a theory of this form which, I mean, does not have speed up over PA, or proving that each theory of this form has a speed up, super exponential speed up over PA. So this means that we need a really slow delta. Right. And maybe the first step in the direction would be to find a theory of this form which does not prove the consistency of PA on a definable cut. So I think that by itself it is not known whether it's such theories do not have speed up, but it's one of the canonical method of getting speed up.
But maybe all this theory of slow consistency would be what.
Yes,
this might be relevant.
This is also a natural candidate. However, there is problem in here that, I mean, I insist that delta should be verifiably in a sigma 1 the same as PA. So so by doing it straightforward in a same, say, straightforward way that I mean, we look on the I mean, if this fast-growing function is not total, then it might cause a problem. Then it might cause a problem. But yeah, I was thinking about it. But it is not. I do not see a clear path in here as well. And I mean, if I may, so there is also one left over from the last week talk, and I mean it is very simple. So we are thinking about. So Ali asked me, or more truly, he caught me on a question which I referred to, on a proposition that I took as black box, and I then couldn't prove it. But there are two sentences which are both independent of, which are both not provable in PA, but their disjunction is provable in PA. So we discussed it last week. So a very simple example is to take the first one, con PA plus incon PA. This is the first sentence. And the second sentence is con PA implies con PA plus con PA. So now none of them is provable by second-Gauss incompleteness theorem, but their disjunction is essentially an instance of a step in Lindenbaum's construction, right? Because if con PA holds, then either this holds or this holds.
Ah.
Right?
Clever.
So
yeah.
That's
right. Very nice.
Yes, and I'm trying to figure out your question. I mean, trying to start thinking about it. But your question about maximal conservative extensions of CT minus provable in CT0, but I do not have any interesting things to say right now. But
there's clearly lots of food for thought.
Yes. Very nicely put. Thank you.
Okay then. So thank you, Mateusz. One more time.
Thank you very much.
I hope to see you all next week, the same place, the same time.
Same time. Okay. Very good. Thanks, everyone.